Okay, so today we're going to be looking at solubility equilibrium calculations. So we've done sort of generic equilibrium. We looked at some gas phase reactions. Then we spent a long section in acid-base chemistry. What's an acid? What's a base? pH, pOH. Then we applied some equilibrium to that. We took a side road on stoichiometry for titrations, and now we're back to equilibrium. And this is the equilibrium of things that precipitate. So if you mix two solutions together and the anion of one solution and the cation of the other make an insoluble compound, then you get a precipitate. So it's a double exchange reaction. You have cations and anions in both solutions. You mix them together and they change dance partners. And if one of those is not soluble in water, it'll crash out. And so we memorize those solubility rules in the first semester. They're coming back today because now we're going to talk about how much those precipitates do dissolve. It's like 10 to the minus 6, 10 to the minus 8 molarity. So it's not much, but if you want to drink that water, you want it to be as low as possible, right? If it's lead and it's 10 to the minus 6, 1 part per million, you probably don't want to drink that. So how could we get that number lower? Could we pair it with a different precipitate or something? And this is used to treat our wastewater. So a lot of wastewater treatment is precipitation. And this is how you would calculate how much of the metals or things that the poisons get past the system. So you don't want arsenic in your drinking water. You don't want lead in your drinking water, mercury. And so this is a way to calculate how much of that will get past your precipitating system. So here's our solubility rules again. Third time we've seen the slide. We've talked about how we precipitate things. We came back to this slide for the acids and bases, and we said if it's a strong electrolyte, cation or anion, like let's take these anions, if it's a strong electrolyte and you pair it with a hydrogen, that makes a strong acid. So the halides were strong acids. There's only a few exceptions to their solubility, and they're cations here. The first proton of sulfate was a strong acid, and so on. So now we're talking about solubility. So how do we want to make things precipitate? Well, these right here, silver, mercury 1, and lead, can be used to precipitate halides. So if you have a system that's producing a lot of chloride or bromide and you want to reduce that load in your wastewater, you want to get those halides out. If you had a source of lead, you could mix those two streams and the lead chloride or bromide would precipitate out and you would capture those. And your wastewater would be cleaner than it was before. If you have these and you wanted to provide some soluble cations, let's say we wanted to plate something in gold and we needed a gold solution. How are you going to get gold into aqueous solution? Well, if you pair it with nitrate, then you can get gold to dissolve. So gold 3+. So gold typically is, doesn't react with things. So somehow at the chemical companies, they get gold to be 3+. They pair it with a nitrate ion. Then they freeze dry that. They suck all the water off with the really cold source. The water vapor pressure goes over it, and they leave behind the gold 3 nitrate. And then they sell it. It's really expensive because it has gold in it. So these anions are how you produce soluble cations. Sometimes, you want to use them to get soluble cations that are not easily ionized, like gold and silver and platinum. These down here, carbonates, chromates, phosphates, sulfides, and hydroxides, those are used to precipitate cations. And so that's where if you have lead in your drinking water or your well water has lead in it, you could run that through an ion exchange column, or you could use a precipitation process and you could precipitate out, say, lead phosphate or lead sulfide, and that would pull that lead load down. How would we get phosphate or sulfide into the solution to mix with the lead? We would pair that with one of the soluble cations, like sodium. So sodium phosphate, sodium hydroxide, sodium sulfide, and then that would pair with the lead. They would swap partners, and the lead sulfide would precipitate out. So now let's do the calculations associated with these. There's about 4 or 5 calculations. Notice I made them full screen for you today because there's lots of little details in the calculations. So hopefully you have plenty of place to write on your paper. So what's the molar solubility of silver chloride in water? Now I'm purposefully giving you things that you have to know the naming for. because I want you to constantly review those naming rules and so on. So silver chloride, silver only forms one cation, so I don't need the Roman numeral. So silver forms silver plus. So, and chloride is 1 minus. So silver chloride, this is the substance here. It's AgCl. And if I put that in pure water, it'll form a very small amount of silver ion and chloride ion. But this is an insoluble substance, so most of it is silver chloride solid. Just a little bit would dissolve. So as long as we have some silver chloride, if any of it leaves, it shows up on the right. We start out with pure water, so we have 0 molar on each of these on the right. And then we have to have some remaining for us to calculate the maximum amount. So this is sort of the criterion of having a saturated solution. So as long as we have some precipitate in the flask, then the silver and the chloride will go to their maximum value, and they'll be in equilibrium with the solid. So everybody understand what's going on. Very little of it is breaking apart, but we're able to calculate how much that small amount is. So we have X here and X here. This is a super easy equilibrium calculation. The KSP is equal just to the aqueous pieces. So that's your equilibrium constant. We do not include the solid. So this is not in the equilibrium constant expression. And the reason it's KSP, that stands for solubility product. It's a product of two numbers, the two aqueous numbers. So we have X times X for those variables, okay? And so then we can rearrange that, and X, that molar solubility, if we lose 1 mole of the silver chloride, that is X, and so it's the square root of KSP. So whatever that KSP is, you take the square root, that's the molar solubility of silver chloride. So we take the square root of 1.77 times 10 to the minus 10, and we end up with 1.33 times 10 to the minus 5 molar. So let's analyze what this means. As long as there's some silver chloride present in the flask, so it's a saturated solution. I'll go ahead and write that out just to reinforce that vocabulary word. So as long as there's a saturated solution of silver chloride, then the silver ion and the chloride ion concentration will be their maximum value, 1.33. Let's say we didn't have enough silver chloride to give us that maximum value. Well, then that tiny little amount of silver chloride would just completely dissolve, and we would have a less than maximum value. They have to reach 1.33 times 10 to the minus 5 for this precipitate to form. And so once the concentration of silver ions and chloride ions, let's say I mix these two together from two different solutions, once that concentration goes above 1.33 times 10 to the minus 5, you start forming the solid. And then you start getting the solid. It becomes saturated and you have a precipitate. So this would be the maximum value, the maximum concentration in pure water at this temperature. So this maximum is temperature dependent. The KSP is temperature dependent. And if you raise the temperature, then the KSP goes up, which means you have a more solution, more concentration. This is the easiest one, so let me clarify anything that you're confused on. This is a good time to pause and look for questions. The reason I say these, yeah. Right, because it's just aqueous. That's where the water is. So when you see aqueous, you know it's in water. And so it doesn't participate in the reaction at all. Yeah. Whereas in acid, it's grabbing that proton. Yeah. Okay, let's go on to now these solubility product constants, they are functions or properties of salts. And so I went and got a whole bunch from the NIST database. The books that you guys have don't have a lot of KSPs. They've got a few. But I wanted to get the ones I wanted to get, and so I had to go to the CRC Handbook of Chemistry and Physics. You can get through this through the Newton Gresham Library. If you go and look for research guides for science, and then you find chemistry, and then it says, it calls it a database. It's really a book, like an online book. And then you come over here on the section of thermo, electro, and solution chemistry, and then you scroll down here, and it says dissociation constants. Let's see, where is it? It might be down below this here, but it's dissociation constants for inorganic salts, or solubility product constants for inorganic salts. And this is these are the tables that I got. Now, I've given you everything on your page, but I want to go through these one table at a time. Okay, so this first table, look what I have here. I have this called MA substances. So metal anion, a single metal. No, isn't that great? Okay, all right. So don't know what happened. A single cation, a metal cation, and an anion. And so that, you see how that's MA? They split apart. They produce a metal and an anion. Okay. So even these that have 4 on them, like SO4, this SO4 is the anion. It's the sulfate anion. So barium sulfate, barium is +2, sulfate's -2. And so this is just the metal cation and the anion. They split apart in water. And these are their solubility product constants. Okay, so here's the equations that go with this. We're going to verify these in ICE tables. So if you don't follow what's going on here, that's okay. I put it on this page for your future reference. Like if you come back to this, you can see the type of substance and all the math associated with calculating its molar solubility. Okay. Notice that the molar solubility is essentially the square root of these KSP numbers. And so if I have a smaller KSP number, I have a smaller molar solubility. So what's the least soluble substance in this table? Yeah, AlPO4, aluminum phosphate. It's 9.8 times 10 to the minus 21. Okay. Now this is a square root of KSP. That's equal to KSP, you can put in parentheses, to the 1/2 power, right? Do y'all know about that? Square root, 1/2 power. Okay. Whenever you have, let's say we have, just for grins, we have x squared, and then that is cubed. What does that equal? X to the what? 2 times 3. Yeah, x to the 6th. So whenever you have something with an exponent, and then that thing has another exponent on the outside, you multiply the exponents, okay? What do I have if I've got 10 to the minus 21, and that is raised to the 1/2 power? That's roughly equal to 10, let's say that's 20, 10 to the minus 10, right? I'm just taking that exponent and dividing by 2 when I take the square root. Let's go back and look at that silver problem. 1.7 times 10 to the minus 10, square root, 10 becomes 5. You see that? So you can just look at the KSPs for the MA substances, and you can kind of see the molar solubility. You get what we call the order of magnitude, the power of 10. So whatever power of 10 it is, that's the order of magnitude. I just want to give you some skills to kind of estimate things. You can do the full ICE table calculation, but it's kind of nice, especially if you're asked, which one of these is the least soluble? You could, in your mind, sort of calculate their solubility. You could say that these all have molar solubilities. This would be on the order of 10 to the minus 10 molar solubility. This half of that would be 2.5. So 10 to the minus 3, a lot stronger than 10 to the minus 10. Okay. What's the most soluble? It would be that one. Calcium sulfate in this table is the most soluble. And it would have a solubility that's the square root of this 4.93 times 10 to the minus 5. Okay, so let's look at the next one. MA2 or M2A substances. Now, what do I mean by that? Well, look at these substances. See here, silver sulfate, that's a M2A. 2 cations and an anion. because they're singly charged, and the anions double negative, so it's 2 minus. Here's an Ma2, a calcium hydroxide 2, so a metal and 2 anions. But what do all these have in common? They produce 3 ions. They break into a metal and 2 anions, or they break into 2 metals and an anion, 2 cations and an anion. They're going to be, we'll get to the ice table where we do this, but you'll see that KSP is equal to this relationship. For an Ma2, it produces X for the metal cation and 2X for the 2A minus. And then when we calculate KSP, that's going to be squared. So that's our equation for KSP. The 2 squared comes out as 4, and then I have X cubed. So I can solve for X. I have KSP over 4 to the 1/3 power. Okay, so we'll do an ice table problem with this. This is really hard to understand if you haven't seen the ice table, perhaps. So let's look at these. Notice that these numbers compared to these numbers might mislead you. You might look to see that, let's try to pick one. Well, here's one that's times 10 to the minus 20. You know, it looks like this one's times 10 to the minus 21, so this would be less soluble than this one, but that may not be the case, because I've got to take this and I've got to take the cube root of it. So 1/3 of 20 is about 7, so 10 to the minus 7, whereas this one, 1/2 of 21 is around 10 to the minus 10. So you have to know what kind of substance you're doing if you're going to compare KSPs for your estimates. And we'll do one for silver. We'll do it 3 different ways, and we'll see how what we might predict from the KSPs would be wrong if we don't take into account the substances. Let's look at some of the other substances. Here's an Ma3. So iron can be a 3+ charge, and if you pair it with hydroxide, which is 1 minus each, you need 3 hydroxides to balance that out. So that's a Ma3. Here's silver phosphate. Silver's +1, phosphate's 3 minus, and so that's a M3A type substance. And here's the math that goes with those. So the molar solubility would be that KSP over 27 to the 1/4 power. And this was neat. As I was digging through the paper, you know, or through the CRC, you know, we say the group 1 cations are soluble with no matter what you put it on. And sure enough, I didn't find anything in that table where you could precipitate sodium. Okay, but I did find lithium, and I thought, oh, that's interesting. So you can precipitate lithium with phosphate. It's like the one example of a group 1 cation that I could find. So sodium, there was 1 or 2 potassium ones, but none of the anions were anything that you'd run across. And so it's pretty rare that you have group 1 precipitates. They form good electrolytes with just any substance. But here's an exception, lithium phosphate. And then there's this weird one that has a M2A3. So like if you couple a 2+ cation and a 3 minus anion, you've got to get the charges to match. So you do that cross multiplication. You need 3 of those cations, so you have a +6, and you need 2 of those anions, so you have a -6. When you pair that together, you end up with an M3A2, like calcium phosphate. You need 3 calciums to give you 6 positive charges, and you need 2 phosphates to give you 6 negative charges. I couldn't find any M2A3s because I couldn't find any. I thought maybe aluminum. It has three charges. It's a cation with 3 positive charges, but I didn't see any aluminum sulfate or anything. Those weren't precipitates. But here's the math associated with that. Kind of a strange formula, KSP divided by 108. Where did I get 108? Well, 3 cubed comes out as 27, and 2 squared comes out as 4, and 4 times 27 gives you the 108. Okay. So let's do these as ice table problems. We won't do all of them, but we'll do a couple more. So here, let's do an Ma2 or M2A type substance. So what's the molar solubility of silver carbonate? So you've got to know your silver ions, so silver +1, and then the carbonate, you have to know what that is. It's CO3 2 minus, CO3 2 minus. So you put those together, you need 2 silver cations to balance the charge on the carbonate. That's the solid. It produces 2 silver cations and a carbonate anion. Oh, I've got a mistake there. I need a 2 minus. Let's keep that. Yeah, we're going to have to replug. That's okay. I want to make sure this is corrected. So put a little 2 in front of that minus as a copy paste error. Okay. I thought I got them all, but I didn't. Okay. I think that's fixed. Let's try this. Nope. All right. So here we are, the 2 silver cations, the carbonate anion. Here's the ice table. It just says in water, so we're going to assume water. So we assume that there's 0 silver and 0 carbonate to begin with. If we lose any silver carbonate from the solid, it shows up on the right as 2x for the silver and 1x for the carbonate. Then we write out the KSP. So that's the silver cation concentration squared and the carbonate concentration. So the silver concentration is 2x at equilibrium. So you have the 2x and it's squared. That's a place where people mess up. They don't know whether you need the 2x or the squared, and it's not or, it's and. Because the concentration at equilibrium is 2x. And then when you write the KSP, it's that concentration squared. So when you square the 2, it becomes 4, and then you can combine the x's, and so we have x cubed. So 4x cubed is the equation for KSP, and then we rearrange that to solve for x. X is the molar solubility. So if a mole of this salt dissolves in water, that's x. Okay. So putting in the numbers, here's KSP. Now here's where you need to know how to use your TI-30 calculator. Because we're to the 1/3 power. I know where the square root key is, but what do I use for the 1/3 power? Okay, this is what you type into your calculator. Okay, it looks pretty complicated. Yeah, you're used to this first part, right? All the way up to the first equal sign, right? 8.46. You hit the double E key to do the scientific notation. You type in 12, and then you hit the change sign, and that makes it minus 12. So that's how you enter 8.46 times 10 to the minus 12. Then divide by 4, divide 4, equals. So then you get what's in the parentheses, you've calculated that. And if you have your TI-30, go ahead and pull it out and practice. It's this piece that's new, taking the 3rd root, okay? So after you calculate the fraction, you hit the second function key and this thing. See, y to the x root. So second function, y to the x root, and you do 3. So you're taking the 3rd root of that equals, and then you get this number here. So if you don't get that number, you're not doing it right.
I have a question. How do you know, like, for the transition metals, which charge they have?
There's no good way. It's a memorized thing. Like copper is 1 and 2, but iron is 2 and 3. Yeah. Now, if I write it in a problem and I say iron 2 chloride, I've told you.
Okay.
It's iron 2 plus. Right? And iron 3 hydroxide, iron 3 plus. Yeah. So, and then if you see this, if you see the formula, like you have iron phosphate, and it's just FePO4. There's no PO4 parenthesis 2 or no subscript on the iron, then you know those charges match. And you know phosphate is 3 minus, so that's telling you the iron is 3 plus. Okay. So is everybody getting this? You're not? It's not working for you?
Well, I see the x to the square root, but I don't see the x to the square root of y.
Can you bring it here? I want to see this. Yeah, let's see, where is it? It's this one here. It's that little guy right there. See, there's a little to the x. Okay, so answer, so then you would do second, this, 3, enter. Syntax error.
That's okay. I'll talk to you about
But that's
after
the
class.
one. That's the one.
Okay.
Yeah. Okay. So I went to the office. They had bought some TI-30s to loan out. And so that's what I was using to make up this little scheme. So, but before we get to that, is there any questions about how to set this one up with the ice table? The place where people go wrong is the 2x squared. They typically mess that up. Okay. And then the calculator. People typically mess up their calculation with the calculator. All right, let's do an MA3 or an M3A. I chose an M3A. This is the molar solubility of silver phosphate in water. Again, from the CRC, that's the KSP for that one. So it's silver phosphate, Ag3, PO4. Here's the ice table. If any of that dissolves, and as long as we have some remaining, it's saturated solution, we'll get the maximum concentrations of these two substances. So if we lose a mole of silver phosphate, we get 3 moles of silver cations, and that would be at equilibrium 3x, and then 1 mole of phosphate, which would be x at equilibrium. So then we have silver phosphate, and these cations, go ahead and put a 3 up here. So this is 3 minus, again, copy paste error on my part. So the phosphate 3 minus, that way the charges match. And then at equilibrium, we end up with 3x cubed. There's 3 of those, so it'd be 3x cubed for the silver, x for the phosphate. When I want to separate the 3 from the x, they're in parentheses, cubed, so I've got to have 3 cubes. So 3 times 3 is 9, and 9 times another 3 is 27. So 27 comes out front, and I have x cubed times x, which gives me x to the 4th. So rearranging that, I have KSP divided by 27 to the 4th power. And so this is when we put KSP in there. This is the calculator, 8.89 double E, 17, change the sign. So that's the scientific notation. And then divide by 27 equals. So that gives me the fraction. Second function, the x root of y, 4, since we're doing a 4th root, equals. And so then that gives me this number here, 4.26 times 10 to the minus 5. Okay. Anything I could clarify on this one? Okay. We've calculated the solubility of 3 different types of substances, MA, MA2, MA3, or vice versa, M3A, M2A. And so let's summarize these calculations. So we have silver chloride, silver carbonate, and silver phosphate. And a lot of times people are tempted to look to, can you put it on vibrate? So if we look at the KSPs and we say which one of these is least soluble, right? Don't look to the right of the table, right? Looking just at the KSPs, which would you say is the least soluble? The bottom one, 10 to the minus 17, because that's the smallest KSP. But you've got to take into account the M3A, okay, and the M2A and the MA. Essentially what you would be doing then looking at these is this one, since it's MA, you're going to be taking the square root. And so you would take this and divide by 2. So this, you would predict that this is roughly going to produce an X that is 10 to the minus 5, right? So I'm taking that 10 divided by 2. Here I have 3 cations, and so I'm going to take this and I'm going to divide this by 3. And so that's going to be 10 to the minus 4. Does that make sense? Okay, and this one, 17, I'm going to divide that one by 4. Divide by 4. 16 divided by 4 is 4. 17 divided by 4 is going to be a little bit more. So, it'll be 10 to the minus 4-ish. We'll say, yeah, 4.25. Okay, so it looks like this one's 10 to the minus a bigger number than this one. So it looks like this one's the most soluble. This one's the least soluble. Just by estimating, knowing how many ions it produces. Now let's look at our results. This was 1.33 times 10 to the minus 5. This was 1.24 28 times 10 to the minus 4. It's a pretty good estimate. And then here's 4.26 times 10 to the minus 5. So which one of these is the smallest number? It's this one here. Okay. So we got 4 zeros and a 1. Down here we have 4 zeros and a 4. And then here we have 3 zeros and a 1. So this one's the most soluble. And this one, this AgCl, is the least soluble. So you see how you have to take into account the type of salt it is. Is it an Ma2 salt or M2A salt? You're going to be taking that exponent of KSP and dividing it by 3 if it's an M2A, because you have 3 ions. If you have a 4 ion or a 5 ion, you're going to just take that KSP and divide by the number of ions you have, just in the powers of 10, that exponent. And then you'll get a good estimate for its molar solubility. Yeah, because there's no way to know them, so you'd have to. Now I may give you all the concentrations and have you calculate it, but you'll be able to find it that way. Yeah. Those, is it always, they're tough questions, right? But yeah, in these types of problems, you have to have KSP or you're sunk. Yeah. So let's add pH to the mix. All right. So everybody comfortable with the ice tables we've done so far? Okay. Notice some of these. Let me go back to this table. So if you want to flip back in your notes, look at this table here. Oops, right. Here. Which one of these salts is going to be sensitive to acid-base reactions? Okay, not really speaking specifically of what type, but which particular species. So not Ma or Ma2 or whatever, but in the table, like what do you see among these different salts that rings a bell of acid-base chemistry? The OHs, yeah. Anything that has a hydroxide, we've got pH, we've got POH, we could add that to the mix. Okay, so if I have an iron hydroxide, it's going to affect water and the hydronium ion concentration, and so I'll be able to see a change in pH. If I have something like silver chloride, it's going to go into water and just be salt water. So it would be pH 7 for pure water, pH 7 for the salty water, because there's no active thing in there that's a weak acid or a weak base or a strong base or anything like that. But if I have a hydroxide, it's going to go into water and it's going to change the pH. What if I have something like a phosphate or a sulfate? So here's a sulfate, phosphate, carbonate. These right here, these anions, are weak acids and bases. So they will act like bases and make weak acids. Now, I said sulfate's a strong acid, but only for the first proton. So as soon as that sulfate comes off, it's going to grab a proton from water and make a basic solution. So it's going to affect the pH. So anything with a carbonate, anything with a sulfate, anything with a phosphate or a hydroxide is going to affect the pH. But the chlorides and the halides, those make strong acids, and so they're not going to affect the pH. Now, fluoride is a weak acid. So of the halogens, fluoride is one that will affect the pH. And that's on your homework, just to reinforce that. So in your homework, one of the answers is like, which one of these salts would affect the pH? And it's a bunch of halides. But fluoride is the one, because fluoride is a weak acid, a weak base. Okay. So let's go on ahead to adding pH to the mix. So what is the pH of iron 2 hydroxide in water? So here I've given you the Roman numeral 2, so you know it's a double cation. So we got iron hydroxide, iron 2 hydroxide, making iron ions and hydroxide ions. So let's go through the ice table, X and 2X. You write out the equilibrium constant expression, hydroxide squared. Put in the 2X, you end up with 2X squared. So it's, again, the same kind of thing. It's an Ma2 type substance, so 4X cubed. I solve for X for the molar solubility. and I do the whole thing with the 4.87 double E 17, change sign, divide by 4 equals. Then I hit the second function, the root key, 3, it equals, and I get this number. Okay, 2.3 times 10 to the minus 6, which again, that's close to 10 to the minus 18, and a third of that is 10 to the minus 6, so that checks out. That's a good way to check your math, too, on your calculator. Does it make sense? So that tells me the molar solubility, but what's the problem asking? pH. What's the concentration of hydroxide ion in the ice table at equilibrium? 2x, right? So this is the concentration of hydroxide ion at equilibrium. So it's 2 times this number. Huge place to make a mistake, isn't it? It's not just x. The hydroxide ion concentration is 2 times x. So hydroxide is 2x, which is equal 4.6 times 10 to the minus 6. Now I can calculate the pOH real easily. I just take the minus log of that number and I get the pOH. And why would I do that? Well, because I know that the pOH and the pH add together to 14. So if I find the pOH, then it's real easy. I subtract from 14 and I get the pH. So this 5.34 is the pOH. Subtract that from 14 and I have the pH. So I added 3 more steps to the ice table problem by getting pH involved. Okay. If you're not doing these problems on the daily, or at least every other daily, it's a lot involved. Look how many steps. You can't just look at the problem and say, okay, I'm going to multiply these 2 numbers and look at the answers. Right? And you got to know what you're doing, because one of those answers might be 5.34, but that's not the pH, that's the pOH. So you got to know why it's right. You got to go all the way and be confident in your answer so that you get the correct one. Yes?
So would you get the same thing if, wait, no, I just answered now. Sorry.
Oh, that's good. No, it's good. That's fine. Any mysteries on this one? I guess the real big conceptual issues, you got X, which is the molar solubility, but then how do I get this guy, right? And so you got to read the ice table. It's 2 times that number. And once I know the concentration of hydroxide, then I can start doing the minus log stuff. Okay? That ice table is really a tool for you to learn what the concentrations are at equilibrium. All right. Let's add a common ion to the mix. Okay, this is the third sort of complication. The first complication is having Ma2 or A2, M2A or whatever. The second complication was just taking the equilibrium concentration and seeing what it does to pH or pOH. The third kind of complication is when you have a substance that's saturated, it's trying to dissolve, but already in the solution you have a common ion. Meaning this substance is trying to produce chloride and you have a salty solution that already has chloride in it. So this is a Le Chatelier's type principle. It's already trying to push against something that's there. So look at this problem. What's the molar solubility of iron 2 hydroxide? And it's not in pure water anymore. It's in a pH 10 solution. Okay, so that's a big difference. Pure water, fine, we can calculate it, but pH 10, that impacts the problem because that impacts the hydroxide ion concentration initially. So look here, initial row. It's one of the few times we've ever messed with that row. The products in the past have always been 0 and 0, but we're in a pH 10 solution, so that is not 0 molar under the hydroxide. In fact, it's 10 to the minus 4. So where did I get that? Well, pH 10, what's the pOH? 14 minus that, okay? So 10, what's 14 minus 10? That's 4. So what's the concentration of the hydroxide ion? It's 10 to the minus 4. So that's where that 10 to the minus 4 came from. I have the pH 10, so that number goes right here. So that's equal to 4. So that's the pOH, and the concentration of hydroxide is 10 to the minus pOH. So that's right there. Okay. I gave you an easy one. It's not like 10.3 or whatever. Just gave you pH 10. So you could easily subtract it from 14 in your head. You know the OH is 4, and then you can easily calculate the hydroxide ion concentration. Okay, so now let's do the equilibrium. So this only works if we have a saturated solution of iron hydroxide. So there'll be some remaining. We have a plus X there. And now we have 10 to the minus 4. Remember these concentrations. What have our X's been? So look through your notes. Give me some of the powers of 10 of the X's. 10 to the minus what? Just look through your notes in these previous problems. 10 to the minus 6, 10 to the minus 5, you know, yeah. And so we have 10 to the minus 4 hydroxide here. That's a pretty big number compared to these others, okay? And it's already a product, so it's going to oppose this X. It's going to really push the reaction backwards. So that's going to make X even smaller. So what I'm trying to get to is I can assume that 2X is small, okay? Because this is a product, it's pushing that reaction backwards. It's actually trying to make X smaller. And so we're going to go ahead and say that column right there is just hydroxide ion. And this makes these problems, the common ion problems, they look more complicated, but calculation-wise, they're much easier. We don't have any square roots or cube roots or to the 4th roots or 5th roots in these kinds of problems because we have one of those numbers. It's not X cubed or anything. When we make the KSP, we have X for the iron concentration, and then we have that 10 to the minus 4 for the hydroxide ion concentration, and that one's squared because there's 2 of those. So this is a really simple calculation. X is equal to KSP divided by 10 to the minus 4 squared, or 10 to the minus 8. So I don't even need to put the calculations out there, right? I can just take KSP and divide by 1, double E, 8, change sign, equals. So X is 4.87 times 10 to the minus 9. So yeah, even if I double that, it's way smaller than 10 to the minus 4. So I can always check my assumption. Go back there, you look at your assumption. I said 2X was small compared to 10 to the minus 4, and it is. 10 to the minus 9 is much smaller than 10 to the minus 4. So that's a good assumption. Yes. Okay, so let's look what happened. When iron hydroxide was dissolved in pure water, there was 2.3 times 10 to the minus 6 moles of that dissolved per liter of solution. Not much, but way more than this. When iron hydroxide is put in a pH 10 solution, which is already basic, which already has a lot of hydroxide ion in it, much less dissolves. And so it's 4.8 times 10 to the minus 9, like less than 1,000th of the concentration. So I dropped the concentration by 1,000 times by just putting it in a basic solution.
So for the tests and subsequent examples, are you okay with us always making that assumption that, oh, it's so small that we can just do this?
I'm kind of torn. I would like for you to be able to do the quadratic formula, right? And on one of these problems, but those take so long. So I'm torn. I don't want you to run out of time. It's a 50-minute exam. Okay. And so I tend to have all of these assumptions be good.
Thank you.
Okay. But that's, I always hate to say that because then you're like, well, I'm never going to do a quadratic formula problem, right? Now I may put one on there that, that if you use that trick where you push it all the way to the products and come back, the assumption's valid and you don't have to do the quadratic equation. But if you don't think through the problem, then you'll be doing the quadratic equation, and it's just, it's because you didn't think about the problem. You got a really big K value, you shove it all the way to the end and calculate how much comes back, and then it's a real simple calculation. We did a really long example in the lecture, so go back and watch that video so that you can know what I'm talking about there. So anyway, if we want, let's say iron was something like thallium, like one of the most poisonous elements known. I mean, the smallest elements that, the smallest concentration will kill you. And And so we wanted to reduce this solubility of that element in water the greatest amount. Put it in excess base, and you just drive that solubility down. Why do you think that is conceptually? Well, let's think. This iron hydroxide breaks apart and gets into solution. There's so many hydroxides that they find that iron immediately and drag it back down, right? And so it's just a statistics game. As soon as an iron atom gets out into solution, there's so much hydroxide, it finds it and precipitates it back out. So it just can't get out of the solid phase. As soon as it comes out, it finds more hydroxide and drops back down. So if you really want to keep this iron out of solution, flood it with hydroxide, and then you'll drive it down. Then you filter off that precipitate, and you've got a really basic solution, which then you can neutralize with something that's non-toxic, like bicarbonate, which it reacts with the hydroxide or the acid, and it balances it with CO2 and so on, non-toxic. And so you can take a toxic element out with strong base, and then you can treat the strong basic solution with something that's non-toxic, and then you pour it back in the river or send it to the drinking fountains. Yeah, it's all good. So that's how we treat a lot of our water, was with precipitation. Okay, so we call this the common ion. You see how the iron hydroxide already had an ion in solution, and so whatever you put in that solution had a common ion with your precipitate. So that's what we mean, and it pushed that equilibrium backwards. All right, I'll see you next time. Yes, hold on. What was that? That last slide? Okay, sure. All right, yeah, I'll take care. Yeah, let me try it on yours. This is a little different version.
I'm confused with like this part.
Yeah, okay, so I'm gonna type a number that I can easily take the third root of. So like 27. If I take the third root, it should be 3. Okay, so 27. And I don't know what that up care thing is.
I think
it's not even on.
I think it's to give exponent.
Oh, okay, yeah. So we'll do 27, and then I'm gonna do second function this.
I have a lesson with that.
Yeah, that's not right. Second function. Okay, so the exponent has to come first.
Okay, so
let me try it this way. So I've got, is that the 1/3 one? Yeah, so 3, second function, that. And then I'm going to do 8, 1, 4, 6. Where's the W or second? Oh yeah, that. And then I have 12. I'll change the sign. Ooh, that doesn't do that.
yeah.
Do you have a backspace? Let's see.
Delete.
Okay, delete. Clear. Delete. Okay. So I'm going to put the minus 12, right? Divide by 4. Okay, so that's all inside that first thing. Let's see what we get. No, we don't get we don't get this.
I don't know. I missed the answer for that one.
Okay. Which one is that? It's the
This should be
third
the
one or the fourth one?
First,
Here it is. Yeah, it's right there. 1.28 times 10 minus 4. Okay, I'll try to figure that out. You try to figure it out. We'll communicate with each other. Okay. It may work also that you do the to the raised to the power 0.333333, which is a third, and of course a fourth would be 0.25, and a fifth would be 0.2. Yeah.
So for the last example with the pH of 10,
Yes.
I kept trying to put in the calculator, and instead of getting to the -9th, I got to the -4th.
Interesting. Okay. This one here.
Yes, sir.
So 17. Huh.
It was 4.887 times 10 to the -12. I put that over.
Oh
10.
wait. 17.
Oh, to the -17.
Yeah.
Oh, I was reading that. Okay.
Yeah, yeah. Oh, it's off the screen. Okay.
I thought it was.
I didn't realize it was slightly off the screen. Okay, yeah.
All right, that makes a lot
17.
more
Yeah.
sense.
Yeah.
Thank you.
You bet.